This lecture covers the first part of probability distribution. So statistics can be simply defined as the study of modeling uncertainty mathematically and its many applications. The concept of uncertainty is inspired by our daily observations, and we also notice there seems to be two components to these uncertain observations. On one hand, there is randomness. On the other, there's regularity. Let's look at example. When you toss a coin, it seems completely unpredictable or random as to whether you will get a head or a tail. So there's a randomness component to the uncertain phenomenon. But on the other hand, in the long run, we know as long as the coin is a fair one, the chance of getting a head is the same as the chance of getting a tail, both being 50%. I will leave it for you to go through the remaining 4 examples to identify for each example the component of randomness and the component of regularity. So now the question becomes, how do we model uncertainty, or how does statistics models uncertainty? And this is actually done by the following 3 sequential steps. The step 1 is we define this concept called random variables. The step 2 is we define the definition of probability distribution. And the last step is we'll use function to describe probability distribution. So in this lecture, we're going to cover these 3 steps one by one with some details. Now let's define random variable. A random variable is a quantity that may assume any one of a set of values with varied chances. Now let's define one variable for each of the above mentioned 5 phenomena. So we use x1 to indicate the coin tossed. So if we get a head, x1 would assume the value of 1. If we get tail, then the x1 will assume the value of 0. For x2, we define x2 as number of heads we get in 5 consecutive coin tosses. x3 is the number of customers that might show up between 9 a.m. to 10 a.m. in a bank. x4 is defined as the amount of rain measured in cubic centimeters that Birmingham might receive on October the 1st. x5 is defined as the amount of time measured in seconds for a ATM transaction. Now let's take a closer look at what we meant by assuming any one of a set of values. So for x1, the coin toss example, there are only 2 possible values, 0 and 1. So the set of values for x1 is only 0 and 1. For x2, number of heads we might get in 5 consecutive tosses, the set of value is shown here. It will be 0, 1, 2, 3, 4, 5, meaning it's possible that we might not get any head with 5 tosses. And then the maximum number of heads we can get from 5 tosses is 5. Now, for the set of value that the number of customers that might show up within 1 hour is actually fairly large. And actually, in theory, the possible number in this set of values is infinity, ranging from 0 to positive infinity, with the only restriction that each of these values needs to be an integer, because we do not allow the definition of half a customer. Now let's take a look at X4, the amount of rain measured in cubic centimeters. It'll be easy to see that the possible number of different values in this set will also be infinity. However, notice that seems this infinity is actually greater than this infinity, because we can count how many values sandwiched between 1 customer and 10 customers. There will be from 2 to 9. So that's 8 distinct values. However, if we try to count the distinct values that sandwich between 0 rand and 0.1 cubic centimeter rand, then we'll find out there are infinite possible values between these two values. Because based on the accuracy of measurement, I can insert infinite number of different numbers between these two numbers, such as 0.009 or 0.099 or 0.0999. You got the idea. But this highlights the fundamental difference between the first 3 types of variables, the first 3 variables and the last 2 variables. The first 3 variables are resulting from a counting process, whereas the last 2 variables are resulting from a measurement process. And this difference differentiates a random variable into 2 types. The first type is called discrete random variables. The second type is called continuous random variable. So the first 3 variables belong to the discrete type. The last 2 variables belong to the continuous type. And notice that for the first 2 variables, the set of possible values are finite. It's 2 in this case, it's 5 in this case. For the third variable, the set of possible values is infinite. However, it's countable. For the last 2 variables, those 2 are continuous variables. The set of value is not only infinite, they are not countable. Now let's look at what we meant by varied chances, which is the definition of probability we will turn to next. So here we'll be discussing the probability, the definition of probability for a discrete variable. We'll leave the discussion of a continuous variable in a later lecture. So the probability of a discrete variable is defined as the chance of that variable taking on a particular value expressed as a percentage. And these percentages can be estimated by experiments or observations. And they are called empirical probability simply because that's how we derive them, from experiments or observations. So next, I'm going to use Excel to demonstrate 3 important concepts related to probability. The first one is probability distribution. The second one is called cumulative distribution. And then the third one is the expectation of a variable. So now x1 is the coin toss variable we defined earlier. 0 indicating a tail, 1 indicating a head. So suppose we conduct an experiment by tossing the same coin 100 times. And out of the 100 tosses, we get 49 times tail. And we get heads 51 times. So naturally, the probability of x taking on the value of 0 will be defined as the percentage 49 divided by the 100 times tosses. And similarly, for 1, the value of 1 will be 51 divided by 100. Now I want to formally introduce to you the convention of this writing. This writing is nothing but a mathematical way to say what is the probability of x, the variable, taking on a particular value, xi. And the reason we use I is to indicate the ith possible value for the variable. And in this case, there's only 2 possible values, so I could only be 1 or 2. So similarly, we can calculate the probability of each value for the second variable, which is number of heads coming out of 5 consecutive tosses. So in this case, our experiment will be more complicated. So in each trial, we need to toss the coin 5 times. And then we need to repeat the same trial 100 times. And similarly, by the same logic, we can calculate the probability associated with each value. So this time we're going to use the formula instead of use numbers. So this way, I will just drag to copy the same formula across the row. So for x3, instead of relying on experiments, we now need to rely on observations. But the same idea is still applied. Of 100 observed Mondays, we can record how many days there are 0 customers show up in that 1 hour window. So in this case, it's 5. And similarly, out of 100 observed Mondays, 20 Mondays, we observe 2 customers showing up in that 1 hour window. So the same idea apply here. we use 5 divided by 100 and then copy it across the whole row. So now the concept of probability distribution for a discrete variable can be simply expressed as a table where the possible value that could be taken on by that variable is listed together with its associated probability. And notice the sum of all the probability will always add up to 1. So similarly, if I calculate the sum of all these different probability, it's always going to add to 1. And even for this one, is close to 1. Look at this, it's 0.96. The reason is there are infinite potential possible value that can be taken on, but the sum of all these infinite possible values will still sum to 1. The next concept is called cumulative distribution. It's defined as the probability that a variable can take on a value that is less than or equal to a particular value. So for the coin toss example, the chance of x takes on a value less than or equal to 0 is simply the same as equal to 0. So you would have 0.49 here. But look at this one. Again, the definition of the cumulative distribution is the chance of x taking on a value that is less than or equal to 1 that would include 0 and 1 both values. Therefore, the probability will be the sum of both cells. So similarly, we would calculate the cumulative distribution for the second variable. Here it will be simply the same as the value above. And here, again, remember the definition is the probability of the variable taking on a value that is less than or equal to 1. In this case, it includes 0 and 1. So we just need to sum up these two cells. And I'm going to again use the dollar sign to lock the column D so that I can drag and copy correctly this formula to calculate the cumulative probability for the remaining values. So I just apply the same logic on the third variable here. And notice that for a variable that has finite possible value to take on, the cumulative distribution will always end with 1, here and here. And here is 0.96 because we did not complete the whole table, simply because the whole table will be infinite, will require infinite number of columns. Now, the next concept is called expectation of x, and to me personally, I think it's the most important concept in statistics, and it's defined this way. It's defined as we use the sum product of the possible value paired with their associated probability. Again, this is calculated by multiply the value associated with its probability. The value multiplied by its associated probability, and sum up the products. And that's why we use the sum product for calculating expectation of x. And similarly, the expectation of x2 will be sum product, the possible values in the first array. Here I forgot to put an equal sign. The sum product, the first array includes all the possible values, and the second arrays pair them up with their corresponding probability. So that's the expectation for x2. And similarly, sum product, the values pair with their probability. Again, keep in mind this is incomplete, because in theory this table will go to the right forever. So in this tab, I want to use a very simple example to explain to you why the expectation was defined the way it was defined earlier, and why it's such a useful and important concept in statistics. So let's say you work as a salesman, and your salary has two components. One is $1,000 fixed wage per month, and the second component is a bonus worth $200 to award it to you if you exceed certain sales goal. And this are the salary you actually took home in the last 6 months. So in January you make $1,000 without the bonus, and in June you make both the wage and the bonus. Now if I'm asking you what is the expected income for July, so I'm going to show you two ways of answering these questions. So the first way is because you either make 1,000 or 1,200. So the first method simply calls for an average of the two distinct values. So that will give you 1,100. So that will be the first answer for the expected income in July. So the second method is I will simply calculate the average of the last 6 months. That gives you a different value. It turns out to be 1133. So which of the two do you think is a more accurate estimate of the expected income for July? I think most of us will agree this one is a more accurate estimate, because it take into account the different probability of making 1,000 versus $1,200, and this simple average of the two numbers failed to take those factors into account. And now let's actually frame the salary as a variable that can only take on two values. One is 1,000, the other is 1,200. And we use the same logic to estimate the corresponding probability associated with these two values. And since out of 6 months we have 2 months with $1,000. So the chance of making $1,000 will be 2 divided by 6. Oh, I need to change this into number. Right, so here again it's 2 divided by 6. And here equal to, because out of 6 months we make $1,200 for 4 of those 6 months. So again, this needs to add up to 1. And again, our previous definition of exploitation calls for using the sum product. Again, I will choose the first array, which include the values, and pair them up with the associated probability. And guess what? The exploitation is the same value as the value that we calculated from the second approach. And that is why that actually explains the reason that we calculate exploitation, or we define exploitation the way we just defined it, because it's simply an average that takes into account their associated different probabilities. And one more thing, the simple average all of us are used to actually used an implicit assumption, which is these two values are equally likely to occur, which is not true in this case. We will now turn to the third step of modeling uncertainty mathematically, which is to use function to describe probability distribution. And again, in this lecture, we are only going to cover the discrete type of variable. So the first question is why we need to use function, and the reason is fairly apparent from our previous Excel example, because a table is simply incapable of describing the whole picture if a discrete variable has a set of infinite values. So instead, we'll try to use a function to replace table to map each possible value to a probability in a very succinct way. We'll next show how this can be done. So here is the probability distribution of the variable representing the number of customers in a bank we have used earlier, and with some modification. So we disallow 0 being a valid value, and compare with relying on observation to estimate probability. Here we further suppose that we could actually know the corresponding probability precisely. And so here, the chance of one customer appear in that 1 hour window is 1/2, which is 50%. And we further know the chance of 2 customers appear is 1/4. And the chance of 3 people would appear is 1/8. You notice that the probability for each number is half of what the preceding number is. So at the end, you have this sequence of numbers that are corresponding to the possible values. And the reason this could be a probability distribution is this sequence of number, despite it has infinite number of values, it will sum to 1. So if you need some convincing as to why this is the case, I prepared this diagram right here to help you grasp that this sequence does sum up to 1. Also notice there's a very nice relationship between the value and the probability, which is the probability is simply raised 0.5 to its corresponding value. So you can verify here for the chance of two customers appearing is half raised to the power of 2. Similarly, for 3 people to appear in that 1 hour window, the probability is half raised to the power of 3. And this relationship holds true for every possible values. And it's written here, and we call this a functional relationship. And that's what this part is trying to convey. It represents this relationship as a function. That's why we use f as the notation convention. And xi is called the independent variable of the functional relationship. And half is called a parameter or constant in this case. So typically we would draw the independent variable in the horizontal axis, and then the resulting value we call as the dependent variable in the vertical axis. And that is how we can use a function to replace a table to describe the distribution for a discrete variable that has infinite number of values. And this type of probability distribution function is actually referred to as a priori probability function, because the probability are derived not from experiments or observation, but from prior knowledge and mathematical reasoning. And there are 3 corresponding a priori probability function associated to the 3 examples that we have been used so far, namely the coin toss, the consecutive coin toss, and also the customers in a bank. And they are called Bernoulli distribution, binomial distribution, and Poisson distribution respectively. And each of them is using a functional relationship to map a valid value to a probability. So these functions are of varied complexity. However, the idea is still the same. It's mapping the possible value to its corresponding probability. And look at the first distribution. It only has one constant or parameter, which is denoted as pi here. And again, if you relate it to the coin toss example, the constant is about whether or not the coin is biased or fair. If it's a fair coin, then the pi is simply equal to 50%. And you can imagine if it could take on any value between 0 and 1. For the second distribution, the binomial distribution, which describes how many heads you will get from multiple tosses, naturally you need to incorporate how many tosses each trial consists. So it requires a second parameter, which is n, that indicates how many tosses that come to form a trial. And for the Poisson distribution, there's another parameter which is noted as lambda. And much of statistics is about how can you derive a priori distribution from empirical distribution. or in other words, how to find the best a priori distribution with appropriate parameters and complexity of the functional relationship to best describe the observations or experiment results, and then how to make inference regarding those parameters. And we will talk more about these 2 points in later lectures.